So we will study superposition of two simple harmonic motions in two perpendicular directions that results in a particular type of motion and a path called Lissajous figure. So motions with the same frequency, that's the first thing that we'll be studying. So consider superposition of two simple harmonic motions on a single particle in two perpendicular directions. What we have written here is the x position given by a1 cos of omega t and y position given by a2 cos of omega t plus delta, where delta is some phase difference between the two motions. At time t is equal to 0, x is equal to a1 and y is equal to a2 cos of delta. Depending on this phase difference, we will have different types of motions. The simplest one is delta equal to 0. Then we have x equal to a1 cos of omega t and y is equal to a2 cos of omega t. That actually gives a straight line motion because you can see y is equal to a2 over a1 all into x. That's an equation of a straight line going to the origin. For the second case, where delta equal to pi by 2, we have x equal to a1 cos of omega t and y equal to a2 cos of omega t plus pi over 2. That is equal to minus a2 sine of omega t. Since one of these is cos and other one is a sine function, this gives us a clue of how to combine these two x and y variables, because we know the identity sine square omega t plus cos square omega t equal to 1. That gives us x square over a1 square plus y square over a2 square equal to 1. This is a very well-known equation of an ellipse. Depending on delta, the sense of traversal of the ellipse will be determined, because we can have the same thing with delta equal to 3 pi over 2. For delta equal to pi over 2, we have this kind of motion where the particle traces out an ellipse in the clockwise sense with the center of the ellipse at the origin. For delta equal to pi over 2, as time t increases, x is greater than 0, but decreases because of the graph of cosine, while y becomes more negative because of the graph of the sine function. You can also see this as x is positive and time t increases, then we have this x is actually decreasing. X is decreasing because cos has a maximum when the argument is 0. So at time t equal to 0, the position of the particle is at x equal to a1 and y equal to 0, which is this point. As time increases, x is still positive, but it goes down in magnitude. And y is negative, and it increases. So we can see very easily that this particle traces out this part of the ellipse in the clockwise sense. Thus, for delta equal to pi over 2, the ellipse is subscribed in the clockwise direction. Similarly, for delta equal to minus pi over 2, the ellipse is subscribed in the anti-clockwise direction. Delta equal to minus pi by 2 is equivalent to delta equal to 3 pi by 2, because we can add 2 pi to any of the cos or sine functions and nothing will be changed, because these are periodic functions with period of 2 pi. The third case is where delta equal to pi. We have x equal to a1 cos omega t and y equals to a2 cos of omega t plus pi. That gives you minus a2 cos of omega t. So this again is an equation of a straight line, y equal to minus a2 over a1 whole into x, which has a negative slope, as we can see very easily, because if x is positive, y is negative. And as s increases, then y also increases in the negative direction. The third case, delta equal to 3 pi over 2 is equivalent to delta equal to minus pi over 2 that we discussed before. And again, we have an ellipse with a motion in the anti-clockwise sense. Consider the fourth case, and actually the fifth case, where delta equal to pi over 4. This is a very interesting case where we have a very simple, very interesting path actually. So x equal to a1 cos of omega t and y equal to a2 cos of omega t plus pi by 4, which we can expand into a2 over root pi cos of omega t minus a2 over root pi sine of omega t. To see the motion, we use a graphical representation. The positions of the points P1, P2 on the reference circle are shown in the number of instances separated by 1/8 of a period, because we are considering pi over 4, that is 1/8 of 2 pi. So we are referring to actually this figure where the first point 1 represents the position of the particle at time t equal to 0. We then have consecutive positions of the particles at 2, 3, 4, 5, 6, 7, 8 points. Points number 1, 2, 3, 4, 5, 6, 7, 8. We have 8 positions that we will trace out. The points are numbered in the sequence beginning with 1 at time t equal to 0. The projections from these corresponding positions of P1 and P2 then give us a set of intersections as shown. So these positions are along the x direction and the y directions, which are the instantaneous positions of the point P as it moves within the rectangle. We get Lissajous figure because x equal to a1 cos of omega t and y equal to a2 over 2 cos of omega t when t equal to 0. That means we have at minus a over 2 sine of omega t. So that means at t equal to 0, we have x naught or x0 equal to a1 because cos of 0 is 1. And y of 0 equal to a2 root pi root 2. That means we have both x as a1. So this is my maximum position of x at a1. And we have y of 0 equal to a2 by root 2, which is less than at least 0.707 times a2. So it's less than a2. So the y position is here. We have maximum value of x at a1, and we have in the y position, let me see, yeah, we have the 0.2. So that is my y position. That is my a1. This is my x by x circle, and this is a circle representing the y. So y is positive, x is also positive. These are two circles which represent the x and y motions on the circle. So as time increases, the position of the particle, the component, the position x position is given on this circle, y position is given on this circle. As you can see, x0 is a1, where the particle has x displacement equal to, along the x direction a1, and along the y direction we have also positive a2 by root 2. It's also positive. So this is the actual point where the particle is at x equal to t equal to 0. The above figure can be represented as a compact form because, as you can see, we can superimpose half of the circle on the other part. So we have a semicircle, two semicircles. One is showing the position along the x direction and other showing the position on the y direction. So we have 0.1 and 0.7. They are on opposite sides of the circle, as you can see. So we can fold this part onto the other part, and we can fold the lower part onto the upper part of this circle of this, yeah. So this in the compact form, we have at time t equal to 0, The x position is given by this point 1 at time t equal to pi by 4 by 1 over omega. So omega t equal to pi by 4, we have the position here at 2, then omega t divided by pi by 2, we have at 3, and so on. This is written here. The paths in the xy plane for a1 equal to a2 and for various deltas are given here. As you can see, we have for different deltas, we have different orientations of the ellipse or of the straight line. And depending on delta, we not only have a different orientation, but we also have different senses of rotation. So what are the possible things? For delta equal to 90 degree, we have a clockwise rotation of the particle on the path that is of this figure. This is a1 equal to a2, so we have a circle. For delta equal to 120 degree, we have an ellipse, but the ellipse is rotated. For delta equal to 150 degree, we have another ellipse, and things like that. So we can have different ellipses and different straight line Lissajous figure, depending on delta and a1 and a2, their relative magnitudes. Using this notation and using this method, we can show that x square over a square plus y square b square minus twice xy over ab cos of delta equal to psi square delta for x equal to a cos of omega t and y equal to b cos of omega t plus delta. This is a more general case where we have two different amplitudes of the motion and a general phase difference delta. This is actually an equation of a conic section. And if we cut the cone by different planes, you will get different types of paths like circles or ellipse or straight line, a pair of straight line, etc. So this is a quiz that we can easily show, very easily. Perpendicular motion with different frequencies. So far, we have been considering omega 1 equal to omega 2 equal to omega. But it's not necessary that these two frequencies must be the same. So we can have two different frequencies, omega 1 and omega 2, and the general positions of the particle are given by x equal to a1 cos of omega 1t and y equal to a2 cos of omega 2t plus delta, but in general, omega 1 is not equal to omega 2. We can take different examples. So let us take omega 2 is equal to twice omega 1, that is t1 is equal to twice t2, and delta equal to pi over 4. This is just a particular example that we are considering. We can again perform a graphical construction at time intervals of delta t equal to t1 over 16. Note that delta t is equal to t2 over 8. So we can take different time intervals, but for convenience, we are taking this delta t equal to t1 over 16 and t2 over 8. Then again, if we put in the values, x not equal to a1 and y not, y tan t equal to 0 to a2 over root 2, very simply, because delta equal to pi by 4. X equal to a1 cos of omega t, y equal to a2 cos of omega t plus pi by 4. In general, we have equal to this thing equal to a2 over root 2 cos of twice omega 1t plus a2 over root 2 sine of twice omega 1t, because omega 2 equal twice omega 1. So using the same construction, x goes through one complete cycle, y goes through two complete cycles. This is seen here. So from 1 to 2, the position of the particle goes from 1 to 2 to 2 to 3 to 3 to 4, 4 to 5, 5 to 6, 6 7 to 8, 9, 8 to 9. This is for half the cycle. So at 1, that time t equal to 0, we have x equal to a1 and y equal to a2 over pi root 2. That's all. So we have maximum position of along the x direction, and we have a2 by root 2, along the y direction, the displacement. So we have this position. We have this part. At t equal to 0, we have this thing. At t equal to delta t equal to t1 over 16, we have x equal to a1 cos of omega 1 t1 over 16, and x equal to a1 cos of pi over 8. So we have to actually calculate this thing using a calculator, because we don't know the value of cos of pi by 8 at hand. I mean, it's not really readily known. So y equal to a2 cos of omega 2 delta t plus pi over 4. So a2 cos of pi over 4 plus pi over 4, that is equal to cos pi, a2 cos pi 2, pi over 2, that is 0. So at t equal to delta t, that is t1 over 16, we have some value of a, x, and 0 value of y. So that's what we have here. This position number 1, position number 2. So in this semicircle, it is moving in the anti-clockwise direction, and in this semicircle, it's moving in the clockwise direction. So as a result, we have this position of the net position of particle on the x-axis, y equal to 0, and x has some value. That means the particle is tracing out the path in some particular sense. We cannot call it clockwise or anti-clockwise because it's not on a circle anymore or an ellipse, but it is tracing out the path in a particular sense. At t equal to 2 pi over 2 delta t, we have t1 equal to, that is equal to t1 by 8. We have x equal to a1 cos of omega 1 t1 over 8. That is a1 by 2. And y equal to a2 cos of twice omega 2 delta 2 plus pi over 4. That is equal to a2 cos of pi over 2 plus pi over 4. And if you do the math, you will get minus a2 by pi over 2. So similarly, we can show that at different times, we will get different positions of x and y. And if you trace out these things very easily, we can do the math very easily. Then we have, for different positions, we have the total path still made this thing. That's the total path. It's a very complicated path, a kind of complicated path, but this is what we have. We can actually see this on an oscilloscope. If you apply two sinusoidal signals in the perpendicular directions, the x and y channels of the oscilloscope, and we feed on the oscilloscope screen. We can perform graphical constructions of similar figures for different deltas. So these are some examples. For omega 2 equal to twice omega 1, we have these examples. For different values of deltas, we have different paths traced out by this particle. Similar figures for different conditions. The ratio is that of the frequencies omega 1 is to omega 2. So for omega 1 equal to omega 2, we have different figures like these. For omega 1 is to omega 2 equal to 1 over 2, we have these frequencies, these figures. We can further draw the figures like this for different conditions. So these can be drawn very easily. So there's a quiz. Identify the relationship between frequencies and amplitude of different the following Lissajous figure. So the trick for doing this is a relationship that we know, that the ratio of the figures is equal to the ratio of the points at which the figure touches the axis parallel to the lines parallel to the x and y axis. So as you can see here, for one example, omega y is equal to twice omega x. So on the x-axis, the figure touches 2 points. In the y-axis, it only touches 1 point. So omega x over omega y equal to the ratio of the number of points at which the figure touches 2 lines parallel to the y and x-axis. Omega x over omega y equal to the number of points that it touches the x and y axis. So omega x over omega y is equal to You see here we have half, that is equal to number of point touches the y-axis, that is 1. You have a number of points touches the x-axis, that is 2. That's the relationship that you can use. Okay, the answer for this case is omega 2 is equal to omega y is equal to 3 over 4 omega x. In general, it is seen that closed paths occur in Lissajous figure only if the two angular frequencies have ratio equal to rational numbers, that is of the form p over q, where p and q are integers. If omega x or omega y is not equal to p by q, then the point would go through all points within the rectangular region and never retracts its path exactly. So this is what we have for the Lissajous figure for the time.